Alright, welcome to section 3 Observatories on Earth. So let's start with a simple question. Why do astronomers put observatories in remote locations instead of cities? Pause here and jot down what you think. Now, one big reason is light pollution. So, what is light pollution? Cities produce huge amounts of artificial light, which brightens the night sky. So, this makes it almost impossible to see faint stars and galaxies. And light pollution is essentially sky glow. So, the sky looks brighter because of all the street lights, buildings, and car lights. And also, those scattered city lights overwhelm faint starlight, making dim objects invisible to telescopes. So, think about your own experience. Can you see more stars when you are in the countryside compared to the middle of the city? What do you think? And even nature can interfere. Moonlight is the biggest culprit. And a bright, nearly full moon can wash out faint objects in the sky. And some kinds of astronomical observations, especially of faint galaxies, are simply impossible during the full moon. So that's why astronomers schedule certain observations around the new moon instead of the full moon. Now look at this figure. It's a satellite view of the United States at night. So notice how cities are blazing with light, while the darker regions like deserts and mountains are where we actually find many observatories. And these remote spots are chosen on purpose to escape light pollution. So the first step in building an observatory is choosing a dark, remote location away from cities and artificial light, and even timing around natural light sources like the moon. So next, let's see how Earth's atmosphere plays a role in observatory locations. Now before we talk about interference, let's briefly introduce radio astronomy. So unlike optical astronomy, which observes visible light, radio astronomy studies radio waves from space. And these waves allows us to explore objects and phenomena invisible in visible light, like pulsars, distant galaxies, and the cosmic microwave background. So think for a moment. Why might studying radio waves reveal things that visible light cannot? Because radio waves can penetrate dust clouds and detect objects too faint or cool to emit visible light, right? Now, radio signals from space are extremely faint, millions of times weaker than local signals here on Earth. So, even something as ordinary as a microwave oven can completely overwhelm them. So, detecting these cosmic signals requires very sensitive equipment and careful site selection. Now, imagine listening for a whisper in a crowded stadium full of people shouting. And that's what astronomers face when trying to detect cosmic radio waves. Since cosmic radio signals are easily drowned out by local interference, observatories must be isolated. And also, our environment adds even more challenges. Car engines, cell towers, satellites, and Wi Fi all produce interference signals. So, scientists reserve narrow radio bands for research, but they can still be contaminated by human technology. Now, how might satellites or cell towers near an observatory affect the data? What do you think? Because they can create false signals or noise, making it hard to detect faint cosmic signals. So, to minimize interference, radio telescopes are located in remote valleys or deserts, where mountains and terrain naturally shield them from human made noise. So, think of this as a dark skies equivalent for radio astronomy, a quiet environment where faint cosmic signals can be detected. Now, why do you think valleys or deserts are chosen instead of mountaintops, which optical observatories prefer? It's because valleys and deserts block human made radio signals better than mountaintops, creating a quieter environment for radio observations. Alright, now let's see why astronomers often build optical and infrared observatories on high mountains. Because mountains provide some of the clearest views of the night sky on Earth. And this is different from radio telescopes, which often prefer valleys or deserts to block radio interference. Now remember seeing. It is the term astronomers use to describe how steady and sharp stars appear through a telescope. So on mountain tops, the airflow is smoother, which reduces the turbulence that normally blurs starlight as it travels through the atmosphere. So this makes the stars appear sharp and less twinkly, allowing astronomers to observe fine details in planets, stars and galaxies. So good seeing is critical for high resolution imaging. And if the air is turbulent, even a large telescope will not produce clear images. Now look at the Mauna Kea summit in this figure. The telescopes sit above much of the atmosphere, where airflow is smoother, giving clearer views of the stars. And also high altitude air is thinner, meaning there is less atmosphere for light to travel through. And less atmosphere reduces absorption and scattering of visible and infrared light. And because of that, more photons reach the telescope. Less scattering, that means more photons. And remember, dry air is essentially important for infrared astronomy because water vapor strongly absorbs infrared radiation. So observatories on humid or low altitude sites lose much of the infrared light before it reaches the telescope. And this is why locations like Mauna Kea in Hawaii or the Atacama Desert in Chile are ideal. They combine high altitude and dry conditions for maximum transparency. But of course, building on a remote mountain top is not easy. It is expensive to transport heavy equipment and construct large telescopes domes at high altitudes. Roads may need to build, and workers face thin air and harsh weather conditions. But despite these challenges, the benefits outweighed the costs. The mountain environment provides clearer, sharper, and more detailed images, which is critical for scientific discovery in optical and infrared astronomy. So, in short, the logistical difficulties are a small price to pay for world-class observational quality. Now that we know why optical telescopes are placed on high mountains, let's look at challenges in building large optical telescopes. So one major problem historical has been the mirrors themselves. Now in traditional telescopes, mirrors had to be made very thick and heavy to prevent them from bending under their own weight. So if a mirror bends even slightly, it distorts the image, making stars and galaxies appear blurry. And heavy mirrors also take a long time to cool down at night. And uneven cooling can create air currents near the mirror, further blurring images. So all these issues limited the size of mirrors astronomers could build for high quality imaging. Now a famous example is the Palmer 200-inch telescope built in 1940s. So diameter of 5 meters, making it one of the largest optical mirrors of its time. And weight is about 14.5 tons. So imagine trying to support and cool a mirror that heavy without distortion. It was a huge engineering challenge. Now here's a historic photo of the Palmer telescope. It has a massive mirror inside the dome which had to be carefully supported to prevent bending and image distortion. So, having heavy mirrors caused several problems. First of all, they were expensive to manufacture and transport, requiring specialized facilities and cranes. And the weight and rigidity limited how big mirrors could be, restricting how much light the telescope could collect and how fine the details it could resolve. So, overcoming these challenges was key to designing modern large telescopes. Now, why do you think astronomers had to balance mirror thickness, weight, and image quality? What would happen if the mirror was too thin or too thick? If it's too thin, then mirrors bends and distorts images. And too thick, then they are extremely heavy, expensive, and slow to cool. So traditional mirrors imposed serious limits on telescope size. Now in the next slides, let's see how modern technologies like segmented and lightweight mirrors overcame these challenges. So modern telescopes use thin or segmented mirrors instead of one huge heavy piece of glass. So thin floppy mirrors are much lighter, cool down fast at night, and reduce image distortion from uneven temperature. And segment mirrors made of hexagonal sections. They are easier to manufacture, transport, and assemble into very large effective surface. So these mirrors let us build much larger telescopes than was possible with traditional heavy mirrors. Now look at this concept art. You can see a modern telescope segmented primary mirror showing the hexagonal pieces fit together to form a single reflecting surface and a thin floppy mirror. Now even with the thin or segmented mirrors, gravity or temperature changes can still cause small distortions. So active optics systems use computers and sensors to adjust the mirror's shape in real time. So this corrects bending and distortion, keeping the image sharp and clear throughout observations. So think about it. How does computer control of mirrors and mounts help astronomers get the sharpest image possible? Because computers can adjust for distortions and track stars continuously, compensating for both mechanical and environmental effects. And telescope mounts also have improved. Old equatorial mounts were designed to mimic Earth's tilt, which made tracking stars mechanically complex. Now modern telescopes mostly use alt-azimuth mounts, which are simpler and fully controlled by computers. So these mounts allow precise tracking of objects across the sky, even with very large and heavy mirrors. So with these modern solutions, thin and segmented mirrors, active optics, and computer-controlled mounts, astronomers can build gigantic telescopes that capture more light and finer details than ever before. Now that we understand modern optical solutions, let's see the largest telescopes in the world today. So these telescopes take advantage of segmented mirrors, advanced mounts, and active optics to achieve unprecedented light gathering and resolution. So most of today's giant telescopes use segmented mirrors rather than a single piece of glass. And these segments fit together like a giant honeycomb, forming a single effective mirror surface. So this design makes it possible to build much larger mirrors than would be feasible with a single heavy piece of glass. So look at this figure. You can see the hexagonal segments forming the primary mirrors in these most giant telescopes. And the Keck Observatory has two of the world's largest optical telescopes. Each telescope has a 10-meter primary mirror made of 36 hexagonal segments. So together, they collect an enormous amount of light, allowing astronomers to study distant galaxies and stars in unprecedented detail. And the next one, the Very Large Telescope VLT in Chile. It consists of four 8.2-meter telescopes, and they can operate individually or link together using interferometry, which combines light from multiple telescopes to act like an even larger one. So this technique allows astronomers to resolve extremely fine details that a single telescope cannot. And the next one is the Grand Telescopio Canaris, which has a 10.4 meter segmented mirror, making it the world's largest single aperture optical telescope. So like the other segmented mirrors, it uses hexagonal pieces to form a continuous surface, allowing extreme light gathering power. So think about this. Why do you think modern telescopes are moving towards segmented mirrors rather than single large mirrors? It's because segmented mirrors are easier to construct, transport, support, and adjust. And also they allow much larger apertures than single mirrors. So these world-class telescopes represent the cutting edge of optical astronomy, combining massive light gathering power, fine resolution, and advanced technology. Alright, now let's look to the future of optical astronomy. Engineers and astronomers are building next generation giant telescopes that push the limits of mirror size and technology. So these telescopes will allow us to answer some of the biggest questions in the universe. The Giant Magellan Telescope uses 7 mirrors combined to form a single effective mirror. And the combined aperture is 25 meters, making it one of the largest telescopes ever planned. So this large aperture allows extremely faint and distant objects to be observed in incredible detail. Now look at the artist concept. You can see the 7 circular mirrors forming the primary surface, highlighting the GMT's innovative segmented design. Next, the 30-meter telescope. It is even larger. It has 492 mirror segments forming a 30-meter aperture. So the huge light gathering area will let astronomers study distant galaxies, stars, and exoplanets that are currently invisible to us. Next, the extremely large telescope ELT in Chile. It will be the largest optical infrared telescope ever built. It is currently under construction in Chile's Atacama Desert, with the first light expected in 2028. And it will have 798 segments forming a 39-meter primary mirror. So with this size, it will provide unprecedented resolution and sensitivity, helping us explore the faintest objects in the universe. Now this figure shows artist concepts of GMT and ELT, Giant Magellan Telescope and the European Extremely Large Telescope. So you can compare the enormous size and segmented mirror designs of each telescope. So these next generation telescopes are not just bigger. They are designed to tackle frontier science questions, studying exoplanets in detail, including their atmosphere, observing early galaxies near the edge of the observable universe, probing dark matter and dark energy, which make up most of the universe but remain mysterious. So why do you think having a larger telescope aperture is critical for studying faint objects or distant galaxies? What do you think? Because large apertures collect more light and provide higher resolution, making extremely faint or distant objects detectable. So now with the GMT, TMT and ELT, optical astronomy is entering a new era of discovery. answering questions that were impossible just a few decades ago. Okay, next let's look at survey telescopes, a different approach from giant optical telescopes. So instead of focusing on tiny details of one object, survey telescopes scan large area of the sky quickly to map the universe. That's why we call it survey telescope. It maps the universe. So survey telescopes are designed for wide coverage, not extreme magnification. And their goal is to observe as much of the sky as possible in a short time. So this allows astronomers to track changes, discover new objects, and build a complete map of the cosmos. Now a great example is the Rubin Observatory. It has an 8.4 meter primary mirror large enough to collect lots of light. And its 3.2 gigapixel camera is one of the largest digital cameras in the world, letting it capture huge portions of the sky at once. Now here's the Rubin Observatory and its massive camera. And it's designed to image large swaths of the sky efficiently. Now Rubin can cover the entire southern sky every few nights, creating a time-lapse movie of the universe. How amazing, right? And this repeated coverage helps detect moving or changing objects like asteroids or supernova. Therefore, over time, astronomers build a dynamic map of the sky instead of just a static snapshot. And the science goals of survey telescopes are ambitious. Track asteroids that could potentially impact Earth, observe exploding stars like supernova and colliding galaxies, and catalog billions of stars and galaxies, providing a massive data set for astronomers worldwide. Now here's a question for you. Why do you think a giant camera is more important than high magnification for survey telescopes? So which one is important, a giant camera or a high magnification? A giant camera lets the telescope capture large areas at once, which is essential for mapping and tracking objects across the sky. So survey telescopes like Rubin shows us the big picture of the universe, complementing the extremely detailed images from giant segmented telescopes. Okay, so let's shift to radio astronomy. So unlike optical telescopes that see visible light, radio telescopes detect radio waves from space, which are millions of times weaker than local signals. And single dish radio telescopes are the simplest way to collect these faint signals. So radio telescopes use large parabolic dishes to gather radio waves from distant astronomical sources. And the dish acts like a giant radio ear, collecting faint signals and focusing them onto a receiver. Now because cosmic radio waves are extremely weak, bigger dishes can collect more energy and detect faint or more distant sources. So here's an image of the FAST telescope in China. You can see the enormous dish embedded in a natural depression. It looks like a giant ball, which is perfect for collecting radio waves efficiently. And the famous Arecibo Observatory had a 305 meter fixed dish built into a natural sinkhole. And it was used for pulsar discoveries and SETI. That means search for extraterrestrial intelligence. But its fixed dish design limited movement, but the large size allowed detection of very faint signals across the sky. Somehow, unfortunately, Arecibo Observatory's giant telescope collapsed in 2020 due to cable failures, and the site is no longer an astronomical observatory. Now next coming up, the 500 meter aperture spherical telescope, which we call as FAST, 500 meter aperture spherical telescope or FAST. and it is now the largest single dish radio telescope in the world. Its dish is 500 meters across, almost twice the size of Arecibo, and fast observes pulsars, fast radio bursts, and maps hydrogen in galaxies, providing critical data for understanding the universe's structure and evolution. So again, here's the question. Why do you think radio telescopes need to be so much larger than optical telescopes? It's because radio waves have much longer wavelengths than visible light. So the telescope must be larger to achieve comparable resolution and collect enough signal. So single dish radio telescopes are powerful, but their size and fixed structure can limit flexibility. Alright, now that we have seen giant single dish telescopes like FAST, let's talk about a clever technique astronomers use to get even sharper images: interferometry. So think of it like using multiple ears instead of just one. By combining signals from several antennas, we can see fine details that a single dish cannot detect. So what is interferometry? Interferometry is the method where signals from several telescopes are combined. Now imagine you have a single dish trying to see a distant galaxy. It's like trying to see a coin far away with one eye. Now add several dishes spread out over kilometers, all working together. So by combining the signals using precise timing and computers, the array acts like a single, much larger telescope. So this boosts the resolution so astronomers can see tiny details in distant objects. Okay, now here's a real world example. The Very Large Array in New Mexico, which we call as VLA, Very Large Array. So it has 27 dishes and each 25 meters across. Now here's the cool part. They can slide along tracks, stretching out to 36 kilometers. So by changing the configuration, astronomers can choose either higher resolution or better sensitivity. It's like zooming in and out with a giant radio zoom lens. And another impressive array is ALMA in Chile. Now see this image, the wide aerial view of ALMA array showing spread out antennas and mountains in the background. And it has 66 antennas working together at millimeter and sub-millimeter wavelengths, which lets astronomers see coal, gas and dust in star-forming regions. And the high-resolution ALMA allows us to map protoplanetary disks and study the birthplaces of stars and planets in incredible detail. Now that we know how radio telescopes and arrays work, let's talk about why radio astronomy is powerful. Radio waves gives us a completely different view of the universe, one that optical telescopes cannot provide. So remember, visible light often can't get through thick cloud of gas and dust in space, but radio waves can pass right through. And that means we can observe areas where stars are forming or where galaxies are hiding behind dust. So radio telescopes lets us peer into these hidden regions and discover processes invisible to our eyes. Now can you imagine trying to see a star being born with an optical telescope? You would just see darkness, but radio waves reveal the entire nursery. And next, optical telescopes depend on clear, dark skies, but radio telescopes don't care about sunlight. They can observe the universe 24/7. And this is a huge advantage, especially for tracking variable events like pulses or fast radio bursts that could happen anytime. So imagine a pulsar that flashes every few seconds. If you could only observe at night, you might miss it entirely. So radio astronomy uncovers things invisible in optical light. For example, pulsars are spinning neutron stars emitting radio pulses. And fast radio bursts, FRBs, are mysterious, intense flashes of radio energy. Also, jets from black holes are best seen in radio wavelengths. So, without radio telescopes, we wouldn't even know these objects exist. And finally, the combination of big dishes and interferometry is the key. Large dishes gather weak signals and arrays gives us high resolution. So together we get detailed map of faint distant objects while still detecting the tiniest signals. And it's like having both a magnifying glass and a giant light collector at the same time. Alright, so with this we conclude the third section of chapter 6. So let's take a moment to review what we have learned about Earth-based observatories. So Earth-based observatories needed the best locations. So optical telescopes go on high, dark mountains to avoid light pollution and get clear, stable air. But radio telescopes go to remote valleys or deserts to avoid human-made radio noise. And next, modern optical telescopes use thin or segmented mirrors with active optics and computer-controlled mounts to build huge, precise instruments. And examples include Keck, VLT or GTC. And survey telescopes like the Rubin Observatory scan the sky repeatedly to track stars, galaxies and the transient events. And finally, radio astronomy lets us see through dust, operate day or night, and discover unique phenomena like pulsars and fast radio bursts. And arrays using interferometry like VLA or ALMA give both sensitivity and sharp detail. So overall, clever location, advanced engineering and modern technology allow us to explore the universe from Earth with incredible precision.